All right, so I think you guys, damped oscillation is a fancy term, but you guys have already seen and experienced this countless times in your life. Like, if you're pushing maybe a younger brother or sister on a swing, you give them a push, and their motion is periodic, back and forth, but they just don't keep swinging forever, right? Eventually, friction, air resistance, eventually they're just going to slow down and slow down and slow down and slow down until the amplitude of their motion is zero. And this would be true if you were to compress a spring and let it go. The spring would bounce up and down, but not forever because of, again, friction, air resistance, what have you. The amplitude would just keep getting smaller and smaller until it stopped oscillating. So the way we model a phenomenon like that in the real world is with a combination of periodic functions and decaying exponential functions. So we're modeling here the vertical displacement of a shock, basically a spring on a vehicle that kind of is there to absorb impact and make a smoother ride for the people in the car. But yeah, the cars and the spring, it'd be really silly if you drove over a bump in the road and then your car just vibrated up and down forever. That doesn't happen to us. It's because, yes, the car will vibrate a bit, but because of the amplitude gets smaller and smaller, eventually those vibrations will stop. So we're going to plot what this function looks like using the skills we have, and then just have a bit of a conversation. And then, that's it. It should take about 10 minutes, and you guys can get on to the assignment. So, let's graph this function. So, first thing, we're just kind of applying our algorithm for sketching. Look for intercepts. This one does have a y-intercept, in this case an h-intercept. We just have to find the value of the function when, in this case, t is equal to 0. And then you get e to the power of 0, which is 1, times the sine of 0, which just works out to be 0. So this function passes through 0, 0. We can add that to our graph. There we go. All right. Let's look for more intercepts. That's like the y-intercept. Let's look for x-intercepts. Now, this is a periodic function. It's going to have infinitely many of them. But let's find a few that we can add to our graph. So we can do this just by having a conversation, really. I don't want to blow all of my space down here, but for b, I'm just going to add a little node here. So h of t equals e to the power of minus, I'm just rewriting the function for myself. That is the function, right? Yeah. So if we're asking when is this function equal to 0, well, exponentials are never 0. So we don't have to worry about that part of the function. Again, these are multiplied. We're just using our grade 10 skills of solving by factoring. Two things multiply to 0, one of them has to be 0. But the exponential is never going to be 0. So all the x-intercepts or t-intercepts here will come from when sine t is equal to 0. And this is like your third course where you guys have been working with periodic functions. So whether it's calculator, unit circle, understanding of the sine function, we know this happens when t equals 0, pi, 2 pi, etc., forever and ever and amen. And also like negative pi, negative 2 pi. But in terms of graphing what this function looks like, so we know that our amplitude will be 0 at pi, and we can just approximate where those are. 3.14, 6.28, 9.42, and those will be all the ones that fit on the graph, but they'll go on forever. You guys okay with how we found those intercepts there? All right. So the final thing we'll do we're going to find some critical points. We're going to find, we won't do the second derivative. I think once we find the critical points and just find their y values, it'll be kind of clear whether they're max or mins. Make sure I use my space well. I'm going to run out of space. I know it. I just got a bad feeling about that. Anyway, so let's find the derivative. So we have a product of two functions, an exponential with base e and sine t. So here we go. We'll differentiate the first function, which is just itself, but it's not just t in the exponent, it's minus 0.5t. So multiply by the derivative, minus 0.5. And then leave the second function alone, sine t, plus leave the first function alone, e to the minus 0.5t, and differentiate the second function, minus cosine. Sorry, the derivative of sine is cosine. I know that. You guys would have told me. All right, and I've been saying this every day. We've been taking derivatives with exponentials. That's at some point it's going to be useful to set that derivative equal to 0 and solve it. So we've actually already have a lot of experience in factoring out these expressions. So we're going to be setting the derivative to 0, and let's factor it in this step as well. So we have a common factor of e to the minus 0.5 times t. And I think that's all the factoring I'll do. What's left over on the inside? From the second term, I'll write the second one first because it's positive. We have cosine t. And then from the first term, we have minus 0.5 times sine t. Okay, and then from our discussion from part B, when is this equal to 0? Well, the exponential stuff is never 0. Never, ever, ever. So therefore, we have to ask, what makes this bracket, what makes cosine t minus 0.5 times the sine of t equal to 0? And we've solved equations like this already in the course, and you guys did some of this on an assignment for me, and lots of practice. So I'm going to just take a pause. I'm going to pause the recording. Resume the recording. Here we go. All right. One strategy we had, I got to unmute the screen. One strategy we had when solving trig equations, where we could just sine by itself or sine by itself, was to massage the equation and see if we can get it in terms of maybe tan, which is what I'm going to do here. So if we rearrange this, we get that cosine t is equal to 0.5 times the sine of t. If you divide both sides by cosine, I'm so going to run out of room. It's okay. You get 1 is equal to 0.5 times the tan of t. And if you get tan t by itself, by dividing by 0.5, you get tan of t is equal to 2. Our calculator will spit out a value of t that gives a tan ratio of 2. So if you guys use your calculators, we should be in radians mode. Our t here is clearly not in degrees, so we're using radians. Approximately, let me get mine too. I've been doing grade 11 math, so I need to get out of radians mode. Radians. I need to get into radians mode. Shift tan of 2. I got approximately, I'll go to 2 decimal places. I got about 1.11. How about you guys? All right. That is the first critical point that we're going to have. But there are more. So let's have a little talk about how to find some more. I am going to try to recover here and make Miss Plattner proud of me with my space. I'm going to draw the teeniest of tiny casseroles over here. Now, I can zoom in so it doesn't look teeny tiny. But you guys can fit this in. You could go on the back of your page, actually. You can do whatever you want. I'm not your dad. But what have we found here? Our first solution, 1.11 radians, is somewhere in this first quadrant. I don't know exactly where it is, but this is 1.11 radians, is somewhere like that in that first quadrant. It's between 0 and pi by 2 radians. It's somewhere in there. If we were thinking of, okay, when is the next time the tan ratio is going to be 2? Well, from grade 11, you guys know the CAST rule, C-A-S-T. The next time tangent is positive is over in this quadrant. And what angle is that? Well, it will be whatever angle it is 1.11 radians beyond the negative x-axis, which will be pi plus 1.11. I'll put T1, T2 equals. So we'll add on from 2 pi, we'll add 1.11. So it's, or from pi, excuse me. So 3.14 plus 1.11. So approximately 4.25 for a second time. That will fit on our graph. And one more as well. So if the tan of 1.11 radians is equal to 2, would you guys agree when you go a full revolution around again and get here, the tan will also be 2, right? So what is that from? It's 1.11 plus 2 pi, one full complete revolution. So let's see what that is. So T3 would equal 2 pi plus 1.11 plus 6.28 equals, and I got 7.39. And I think that's the last one that's going to fit. So we had that discussion. We used the CAST rule. We used our calculators, first of all, to get 1.11 radians. And then we just used the CAST rule to get 2 more. Are you guys okay with that? So we've had this conversation. This video will be posted. So if you are looking back and studying this and you're like, okay, where'd those other 2 times come from? You guys can go look at the record here. Okay, let's wrap this up. So those are the times when we'll have some local max and mins. So how high, how low do those amplitudes get? We just need to do a little bit of calculator work. So can you guys crank out, well, what's the height after 1.11 seconds? What's the height after 4.25 seconds? And what's the height after 7.39 seconds? That was the last one, yeah. We'll get those displacements. We'll add them to our graph, and we'll get a good idea of what this graph looks like. And then we'll just have a little conversation to wrap it up. If you guys were working at home, this would be a great problem to make Desmos do. Type in the function and just have it crank out these values. We'll use our calculator. So e the power of negative 0.5 times 1.11 equals times sine of 1.11 equals. So I got about 0.51 centimeters for that one. And I got about negative 0.11. Oh, are we in meters here? I should look. It is in meters. Excuse me. So that's like 51 centimeters, about 0.51 meters. And then we're going to be below negative 0.11. Did you guys get those too? Okay. And then the last one, it should be pretty small. It's going to be close to 0. Yeah, I got about 0.02 meters. How about you guys? Okay, let's wrap all this up. So our first critical point, about 1.11, 0.51, right about, whoopsie doodle, right about somewhere around here, roughly. And then our next, so hopefully you guys would agree, very clearly a local maximum. And then 4.25, negative 0.11, 4.25, negative 0.11, somewhere here. And then the last one, around 7.4, 0.02, so barely above, something like that. And if I were to connect these with a smooth curve, which will test my fine motor skills to their max for sure, this graph would look something like this. So it's kind of periodic. Already screwed that up. It's periodic in that it keeps coming back to this axis, but the amplitude, it's not quite periodic in that the amplitude is changing. I think that's about the best I can do. I'm going to add one more thing into a second here. But you can see the spring initially, huge displacement on the spring, but very quickly comes back to equilibrium and settles, which is exactly what you want when you're driving in a car or if you mountain bike. What you want in your shocks is they absorb that initial compression right away and go back to normal. Because it'd be pretty horrible to be driving around and you hit like, what do they call those? Like a speed bump in the road. And then for the next 2 minutes, your car is bobbing up and down. Like I would get sick because I just get sick that way. What you want your car shocks to do is have that huge displacement and then settle back very quickly. The last thing I'm going to add to this graph here is the following. If you were to ignore the sine t part and just sketch e to the power of negative 0.5 t, this is a super rough sketch, but it would look something like this. It'd just be a decreasing exponential. Looks something like that. And if you plotted...
Can all members of the cross-country team make their way down to the gym, please? Thank you.
Kind of the reflection on the other side. I'm just going to add a dashed line. Kind of like that. Something like that. These functions modeled by these damped oscillation models are basically, you've got a sine function that hits is kind of bounded by these exponential functions, this decreasing exponential here, and then a mirror reflection. And so if you can imagine those two graphs, the function will just go up to a maximum and touch that boundary, and then come back down below and hit that boundary, and go back up and hit that one, and just keeps going down and down. And because these guys have that horizontal asymptote at 0, your function will just keep bouncing between those, but it will approach that asymptote as well. So that's how damped oscillators are modeled in the real world. And the math behind it, for the most part, you guys can do all the math behind it now. So I thought that'd be an interesting thing to do, just to kill some time. And just one last thing, tying everything together. That, unless you guys have any questions, wraps up the calculus portion of our course.